Well, so last week we looked at some of the packages in machine learning. So today we are actually going to look at, building a predictive model. And in doing so, I need to explain certain terminologies and certain things in terms of pipelining the data into creating a model, for prediction. So first of all, if you remember when we started, I made mention that we have two sets of data. We have two kinds of data. There are others, but of course, generally we have two kinds of data. We have the textual data and also the numeric data. So with the textual data, like the Twitter data, text, we have a different approach of handling or building a predictive model based on this kind of text or this type of data. That one is purely, an application of NLP techniques to do that. You have to go through different processes in getting it predicted. Then we have the numeric data, which is the commonest data that we use in our businesses or organization that we collect in the sectors that we work, in the banks and all that. Mostly is numeric data. Numeric data also has a different approach of handling that. Now, today's lecture, of course, this course, software engineer, I decided to bring this part just to give you a gist. And if you are interested in building more knowledge in that area, you can explore. So we are going to handle only the numeric part of it. And then if there is, of course, there's no time, this is the last for the semester. But you can further, you can go and explore the NLP for the text data. That is if you want to build more capacity in this area. So with the numeric data, for instance, yes, if I have a data like this, maybe age of people, different data, and then let's say it's a data about diabetes. Eventually, you want to find out the status, whether the person has diabetes or not. And then I keep saying that data mining, which leverages or which uses machine learning techniques to be able to build a predictive model. When we talk about predictive model, it means that a model that you build or you develop based on the historical data, the existing data you have in your organization, you use that data to train an algorithm so that when a new data is coming, it can be able to predict based on what the algorithm has learned. So for instance, you so happens to work in the bank and someone wants to come for a loan. You can build a predictive model with any of these algorithms so that you have historical data, you have used that data to train the algorithm. So another person is coming for a loan. So based on the details and information you take about the person, when you supply it into the new model, the model that you have built, the model will now tell you that this person is likely to pay the loan back or not. So today, our focus is on how to build that predictive model. Now, the same way, when I started, I also made mention that even with this ML, we have the supervised one. We have the unsupervised. I remember, was it last week or last 2 weeks? The supervised one, that is where you need data that is tagged. So if I have attributes of a data, at the end of the day, I should have tagging, whether, for instance, I'll put data here, the age, BMI, and all that. So at the end of the day, I should be able to know the status of the person, whether the person has diabetes or not. So once you have the status or the label or the tag to the attribute, then you are doing what we call supervised learning. An example is what we call the classification. For the unsupervised, there is no tag. You don't know the status. It's just the data attribute. All you are doing is to throw in an algorithm to look for patterns within the data. So you can imagine, so you can see that machine learning is quite broad. So we can't do everything. This one is even touching them one after. And then there's another one we call reinforcement learning, which emerged not long ago. It's not even more than 5 years. So reinforcement learning is where an agent will also snooze or try to understand the environment, pick the data itself and make certain decision by itself. That's reinforcement learning. It has also come to stay now. It's one of the areas that people are exploring. But our focus this morning is going to be on supervised learning vis-a-vis classification. Okay, so let me quickly give some brief overview. Please, if you have questions, you can ask. Another view of the classification pipeline. First, you need a data, and this data must be a tagged data. For instance, if it is the bank, you have personal information about customers. You have their transaction, activities with the bank. At the end of the day, a particular customer has taken a loan before. When he took the loan, he paid. So in this case, the status, based on his personal information and his financial transaction, the status is that when he took the loan, he paid it. So that's the status, he paid. So we can use a 1 to represent paid. There's another person who also took loan. He has his personal information and all that, but the status is that he did not pay. So we have the status, which is the label or the tax, and then information about the person. So when I have the tax and the information about the person, then we say that this kind of data can be used for classification, meaning that it can be used to build a predictive model. So that based on that, we can use to also predict future happenings or people who will be coming in to collect data. Now, to build a predictive model, this data, there are several techniques to handle this data. One, we have what we call test train technique. Test train. Then another one, this is the commonly used one. There are other approaches anyway. We call it cross validation. I'm going to explain all these terminology because I'll be using them when I'm writing the scripts. Cross validation. So let me ask the class if there's anyone here with knowledge about test train and cross validation. Let me pick someone. Preston, are you here? Preston, are you in class? Preston is not here. Philemon, do you have any knowledge about test train and then cross validation? Any of them at all is okay if you want to explain any of them.
Yes, Doc.
Yes. So which one are you going to explain? Or you want to explain both?
Yes, Doc.
Yes, I'm listening.
So normally you split the data set into maybe percentage, let's say 70-30. Then you use the maybe the 70 to do the prediction, and maybe you use the 30 to do the training.
Usually, you are right. You're right, but it's from the other way around. The 70, the large portion of the data for the training and the small portion of the data for testing. What about the cross validation?
Yeah, cross validation is when you use other data to also validate the model.
Okay, let me explain that. All right. So now, for the sake of others, with the test train, so you have the data here. Let's say this is our algorithm. An algorithm, which we also refer to as the machine. That's why we say machine learning, because you are giving the data to this machine to learn. So the machine is still the algorithm. Now, this data, we split the data into two, depending on what you want to do. I can say that let me split the data into 20 and also 80%, 20% and 80%. So now this 80% is going to be training. We are going to use to train the machine. So you pipeline this 80 and give it to the machine to learn. Now this 20 is used to test whether what the machine has learned is good, it has good accuracy or not. So if I give this data to this to learn, then I realize that the accuracy is just below, let's say, below 50. No, the threshold is 70. Below 70, then I can say that the performance of the machine or the algorithm is weak. So to only the 20% of the data is used for testing, and then the 80% is used to train the algorithm. Mind you that even with this 20%, the data comes with X and then Y. Meaning, we can also put it this way: Y equals to F of X. What this means is that the X is the attributes and the Y is the output, or in other words, the label or the tags. Just like I did explain that, with banking sector, you have personal information about the customer, whether he paid the loan, whether the customer and all that. But whether he paid the loan or not, that's the status. That one's the why. And then the inputs are the personal information, his transaction with the bank. It comes with it. So the 20% comes with this too, and then the 80% also comes with this too. So you give this 80 to the machine to learn. It will learn it, and then eventually, after learning, whatever it is creating is what we call a model. Now, once you have the model, you pipeline the 20% to the model to see the output. So, okay, let me see. There's a chat. Someone testing in the chat. Okay, so who is this? Okay, that's fine. Okay. Now, another way is that the pipelining. Here I have the data. So after the data, we need to see whether, even the next step, you need to clean the data. But today I'm not going to talk about data cleaning. Data cleaning can even take more than a month. So you need to clean the data first. After cleaning the data, the next step is where you need to see whether you are going to use the cross-validation or the test train. So let's assume that you are using test train. Okay. So meaning that after the test train, and this is so the training can be here, and then the testing will be here. Let's put testing here or test here. So the testing data. So let me cancel this test here. So you take the training data and give it to the machine learning algorithm. So let me put ML here, algorithm. Now, after training the machine learning algorithm, output that will come out here is a model, because you have trained the algorithm. Algorithm has learned it, so it is a model. Now you give the test data to the model to see. So the model will now give us the prediction. So this is the pipeline, a typical pipeline. It would give us the prediction. So sorry, the prediction, of course, in the form of evaluation. Now, you can also go with the cross-validation, and research has shown that cross-validation produces more accuracy and better results than the test train. Personally, I've been using cross-validation a lot, but today, if there's time, I will demonstrate both. And then when we talk about cross-validation, let's say that this is your data, and this data, you have instances of a data, and the instances of the data is 1,000 instances of a data, 1,000 of them, meaning that every line of the data, you count them, there are 1,000 of them. Now, what cross-validation does is that you would divide you would define the clusters. How many? Just a minute, who is this? Sorry, just a minute, who is this? Okay, so with the clause, this is how the clause validation works. You see that you have 1,000 instances of a data. You define the number of clusters or the number of validation you want to make. You can say that this one, we use K. In other words, the cross validation, we say that K-fold, you can also call it K-fold validation. What it means is that you have to define the number of K. I can say that let K be 10. If K is 10, what it means is that this data, which is 1,000 instances of the data, you're going to divide it into 10. I think 10 is too much for me for now, for the purpose of training, but mostly we use 10. So let's use 5. So 1, 2, 3, 4, and then 5 of the same sizes. Let me take this part. Let me erase here. Okay, so of the same sizes, so because I divide into 5 here. So 1, 2, 3, 4, 5. So let me ask this question. If I divide this 1,000 instances of the data by 5, what would I get? 1,000 divided by 5 will give us what? Is it 200? So meaning that each of the K, this one is 200, this is 200, this is 200, this is 200, this is 200. When I define K to be 5, so they are all 200 each. What happens is that you take this 200 with a cross validation. This is how it works. it takes the first 200, which is, let's say, x1. Let me use x1 rather instead of the volume. It will take x1 here, x1, and divide this x1 by, so this is x2, this is x3, x4, and then x5. So now it will take x1 and divide it by the remaining data. So meaning that it will be x2 plus x3 plus x4 plus x5. So that is for the first one. The results that will come out, let's say Z1. So after that, it will also take the next cluster or the next key, which is x2. So meaning that you have x2 here on top, divided by, this time you are not going to include x2 here, so it will be x1 plus x3 up to x5. Then the results, let's say Z2. So at the end of the day, you do that for all the 5. So meaning that, you know, we should have something like Z5. Then after that, it will find an average of this one and give us the output. So in this case, it will be Z1 plus Z2 plus Z3 plus Z4 plus Z5 divided by 5. And then the results will give us the output. That is the k-fold validation. So if I define the k to be 10, sometimes if you are building a model, you need to be manipulating the k. You can take it to 5, you take it to 10, you take it to 7 to see which one will give you the best accuracy. Like I said, k-fold validating better accuracy than the test train technique. So I am going to start with the validation. Please, there's noise in the background there. I don't know where it's coming from. Okay, so please, any question on these terminologies? Any question? If there is none, I'm going on. And frankly speaking, I'll bring question around this area. For instance, I may ask you to write something about maybe cross-validation, or what the difference between test train and then cross-validation and all that. So I expect you to do more.
Hey, wow, okay then.
Yes. So a lot of questions will come from this lecture to this lecture. So I expect you to also, not anything, let me know. Okay. So
yeah, hello, Doc.
Yes.
Come again,
Please,
Doc.
okay, then maybe we should go back again so that.
No, I'm not going back. So because because I didn't talk about exams, I know that many of you are not paying attention. Don't worry, I'll move on.
Oh no, we are. I wanted to ask question, but since somebody said you should go back, probably to answer my question.
No, I didn't hear anyone saying that I should go back.
Oh,
Doc, I said I was saying if we could go over this cross validation something.
Okay. Because I said exams.
So this one is there.
All right, so let's move on. So we have well, so if I'm even doing it, building the model, it will come. Okay. So we start. If you remember last week, we started doing something, and I asked you, I gave you a data, I gave you the data. I don't know whether it's this class, and I asked that where you are building the project, where you have saved the project, you put the data in Piman Indian data set. I gave the data to you. So the same way, we are going to play with that data. And the data is, what do you call it? Let me open this data when you see it. Okay, so if you can see, please, can you see the screen?
Yes, Doc, we can see.
Yes.
Okay, so the explanations I was giving so far is that the preg, this is the data from preg, data from plus, data from press, skin, test, mass, pedi, age. So these are the Y, the X, the input data, the X, and this is the label. So Y here and then the X. So these instances of a data, I think there are 769 instances of a data. All I'm saying is that with a k-fold validation, this 700, and if you define k to be 10, we divide this data into 10. And then if you are using test string, all you need to do is that maybe 20% could be from here to, let's say, 70 something. That is maybe 10%. So you give that 10% to as a test data, and the remaining 90% for training. So you can define how you want it to be, how you want to divide the data for the test string. But with the cross validation, you need to divide the data. You define k to be 5, meaning you are dividing the data into 5. So first, you use the first one of the 5 as a test data, and the remaining becomes training. Then you take the second one as test, the remaining becomes training. When you finish, you find an average of the results, and that will give you the outcome based on the cross validation. Now we are going to also manipulate and build a predictive model for a diabetes data here. So I start. Okay. So first of all, we need to load our data, and to get the data loaded, we need to use certain packages to do that. Certain packages, and last week I remember I did explain that. So first of all, we need pandas. So we say that import pandas. So import pandas here, because last week we installed all those packages. Then we also need read. We need read underscore CSV, which will help us to be able to read and import the data into our project. So, and then read underscore CSV is from pandas actually. So we say import read read underscore CSV. Coordinate that is it's a CSV file. Okay, let's leave it for there. Let's leave it for now. We will import more data. So I introduce the hash symbol and say import packages. Okay, so I move on here. So now we are going to load our data. So we say hash here, load data. All right, so first of all, we declare a variable. Let's call a variable file, and this variable file, we put our data in. If you remember last week, or let's say here, the name of the data is pima-indians and the .csv. So let me copy this directly from here so that I'll not make any mistake. Then you put that here, but make sure that you add a CSV because it's a CSV file. Okay. If you want to import, test file, TST file, there's also a different way. You don't use the read CSV to import that. Please, you go and explore that as well. If you are using a different, file format. So after reading it, after putting the data, the name of our data or the data into file, the next step is that we need to read the file. So we can declare another variable and call it data. Then we say that we use the read underscore CSV, this package, to bring in our data. And the data is put into file. So we put file here. We did this one last week. So now we have our data in. So if I say print, and put file here, meaning that it will print our data for us. So let's do it and see. Okay. It says, okay, so import read CSV module name read CSV.
Doc, I think you would import it from pandas.
Yeah,
From
pandas.
pandas
Yeah,
imports.
you're right. So okay. So import. So we say that from. We say from pandas. We did it last week. Import. These people are giving me pressure. So import from pandas. Import read underscore c. Okay, good. So now we run this, and then it's okay. So we have file. No, we rather print data. We don't print file already. So we are now reading it into data. So data, we run this. So this is our data. So we have been able to get the data into our project now. So we have the preg, plus, press, skin, test, mass, spelling, age, and then label. You remember last week we did a lot of manipulations with iLock and what have you. Okay. So now the data is imported. Now the next step is that in machine learning, you need to scale the data. If you remember, I think I did explain this one last 2 weeks or 3 weeks. Scaling is very important, or standardize or normalizing the data is very important. The reason is that if you don't standardize or scale the data, it may create some sort of bias. If you look at PEDI, the range of data is just 0 point this, 0 point that. I think it's not even up to 1. But if you go and look at plus is 148, 85, and then you say this one has a different range of data. So there is a need for us to standardize or scale the data into a specific range. So we can scale the data into a range of 0 to 1. So automatically, all these data will be scaled between 0 to 1, which is very important in order to avoid biases. So we say that scaling data. Okay, how do you scale the data? Now we have the data in, so let's scale it. First of all, we define a variable. Let's call this variable values. But even before we scale it, this table or this data is in a table form, a data frame, because we use pandas. So it's in a data frame. So our interest, we are not interested in the whole table, because if you want to, you cannot manipulate the data if the data is in the table form. We are going to extract the values. We are interested in only the values from the table. So for instance, you have columns and rows, and in it, you have values like the system, whatever in it. Our interest is just the data, the object view, the data in it. So we need to extract the data out before we can even scale it. So to do that, let's say that since we are interested in the values, so let's say declare variable and call it values. And then these values, of course, the data is now what we call it data, we now have it as data, not file any longer. So data. So we put in here, so we say data dot value, meaning that if we use the value function, meaning that we are actually extracting values, only the values from data. So now let's print values and see what we're gonna get. So we are only extracting the values. So our data now becomes this. So we have extracted only the values from the table. So these are the values. You cannot scale it if you don't extract the values. Now the next step is that I'm not interested in printing this. The next step is that we are now going to scale it. And the scaling, we only scale the input data. We don't scale the Y, the label. Only the input that you scale. You don't scale the Y. So we are going to scale the input. And you remember last week, we did how you can be able to even extract this from the table. So our interest to extract that. Okay, you can use the iLog, or you can just go straight and just use the indexing strategy, the direct indexing strategy, to just get the data. So we can say that let's declare a variable. Input is X. So our input variable, which is X. Okay, let me rather make this one extracting values. Extracting only the values from the data. Then I'll come here and say that scaling. So I use the hash, it says scaling. Okay, so now our input, which is x, we've been using x, and now the data is in variable called values. So we say value dot. No, because it's values, because we are going to, index it. So just value into, so comma, you remember that the first one is row, comma. So if I indicate this column here, meaning that I want all the rows to be outputted, you are not actually dividing, only as for the rows, you want everything to come. But it is only the columns that we are extracting the input variables. And the input is from 0, 1, 2, 3, 4, 5, 6, 7. But remember I said if it is 7, we include the 8, meaning that we want from 0 to 8. So the 8 is not actually outputted. So if I print x, so if I say print x, meaning that we are going to bring out only the input variable. So this is the input variable, the input attributes. So you look here, we have 0, 6, 148, 72, which ends at 50 here. So the same way, the 6. Okay, so this 0 is just numbers. So it's just the number. So 6, 148, 72 up to 50. You see that the 1 is not included, meaning that we have extracted only the input variable. We are also interested in the y. So let's come out with the y. So what then is our y? Y is what? 7. What will be y? Y will be column, comma, right, and an 8. Is it correct? Please, are you there?
Yes, okay.
Yes, yes.
Yes, Doc.
Very good. So I'm even asked you to write the whole of this in exams, and I know how to formulate the question. Just write it and I'll follow the steps and mark it. Okay. So I I print it. So
Hey, Doc, you are scaring me.
I want you to follow. Let's print y and see. So y is this. So when I print y, you see that to bring only the 0, 1, 0, 1, 0, 1. So that is 0 means the person has no diabetes. 1 means the person has diabetes. So we are not interested in printing this at the moment. So now let us now do the scaling. So the scaling, let's use the variable. Let's call a variable. Let's declare a variable called scalar. Scalar. So scalar is equals to. Now there is a package from Sklm. You remember when we started, I said Sklm is a whole package which has a lot in it, and in it we have the model selection package and all that. They are all sub packages within. So there is one sub package we call minimum maximum scalar. That is what we are going to use to scale our data, to scale it. So minimum maximum scalar. So it is small m, max, then scalar. So minimum maximum scalar. So with the minimum maximum scalar, we need to define the range for which we are going to scale this. So if I open this parenthesis, then we say that we have a feature within called feature underscore range. So what is our range? Meaning that we are going to scale it between from 0 to 1. So meaning that the data cannot be scaled beyond 1. So if it's 148, we are going to scale it within 0 and 1. Okay. Now, but the issue is that this one is problematic because we have not imported minimum maximum scalar. Let me show you something. I'm going to, if you want to learn more about machine learning or Sklm, there is scikit-learn. Here, everything that you need to know is here. So for instance, if you go to user guide, what do you want to know? Linear models, support vector machine. These are all machine learning classification. Naive Bayes is an algorithm. Decision tree is all algorithms. And I'll talk a bit more of them. Now, You can also go to the APIs and then check some of these. Now we are going to use minimum maximum scalar. You can just Google it. So MX scalar. Okay, in Sklm. Okay, here. So when you Google minimum maximum scalar, if you know what you are using, then you can come here. Sklm will give you all the manual and the information you need to know. It's more or less like a class. So where do I import? How do I get minimum maximum scalar? First, you need to import it. So minimum maximum scalar is within Sklm, a sub-package called pre-processing. So you have to define the range. In our range, we are going to use 0, 1. And of course, we have the copy through and all that. So you can read and understand what we mean by copy, what I mean by clip, then the various attributes, what is the minimum, what does it mean, and all that. So if you look at this part, this is where it is imported. So from skln.preprocessing, import minimum maximum scalar. So here, let me copy this and take it to our project. So here, if I don't import this, so we say from skln.preprocessing, import minimum maximum scalar. If you don't do that, this one will not work. So let me copy this, and then for the avoidance of making any type. Okay, let's go back. See how it is used. So you have, of course, minimum maximum scalar. So you have I define scalar is equals to minimum maximum scalar. Then you open this parenthesis. Then you put in your condition. Here it didn't actually put any conditions, but we need to define the range. And then we are saying that the range should be from 0, 1. It's not compulsory. You have to satisfy all these conditions depending on what you are doing. Okay, so let me go back to our projects. So we are now saying that it should be 0 and then 1. Okay, so after that, the next step is that we need to now we are going to fit the minimum maximum scalar on our data so that, when we click on print, we get the outcome or the output that we want. So let's fit it. We need to also define a variable. Let's call this one scaled. There is a difference between the scalar and scaled. These are all variable. So we are going to fit scalar on our data and I put it into a variable called scaled. So in this case, we say that this scalar, we are going to fit on our data. We say the scalar dot. There is another function, package or sub-package we call fit transform. So we are going to fit the minimum maximum scalar on our data, then transform it. So when you fit and transform, meaning that it should be able to convert, or let's say change from the original data into the range of 0 to 1. So once you put full stop there, then you click on fit transform. So fit transform. And then here, this is where we need to supply our parameter or the argument we are giving. We are fitting scalar and transform it on our X. This input data. So X. So let's put X here. So now, if you do that and then say print scaled, so we're going to print scaled. If you print scale, then it will fit and transform all our data, this data, into only the input data, because we are only scaling the input. We are not scaling the output. It will a range of 0 to 1. So let's run it and see. So you see that you have 0, the first one, which is supposed to be 6, is now 0.35, what have you. Then the last one, which is supposed to be like 60, or is it 50, is now 0.48, what have you. So the data has been scaled all to a range of from 0 to 1 in order to eliminate some biases because of some of the data, the range is different from the others. Okay, so now that we've been able to scale our data, the next step is that we are now going to build a predictive model. If you remember, so let me put hash here.
Dr. Awuni,
Yes.
sorry, but I still don't get the scaling part.
Okay.
Can you please explain the general concept to me? I'm really trying to follow, but I don't really get it.
All right, that's fine. That's fine. So let me explain that. Let me go to our open board. You see, all I'm saying is that let's assume that you want to do some sort of analysis. Where is my open board? Sometimes we use the word standardization, either scaling, standardize, or normalize. Where is this open board? I want to have, okay, it's here. Now, this is what I mean by the scaling. You see, let's say that we are talking about, let's assume that we are collecting data about some people. First of all, we are collecting their age, and then we are also collecting data on their, let's assume BMI as an input data. And let's also see that we are also collecting data about the height, their height. Now, let's say the age range, you have the first person, his age is 96. The second person, his age is, let's say, 24. The third person, his age is 76. Let's look at the BMI. Assuming the BMI, of course, I'm not a medical person. Kristen can correct me, but let's assume the values I'm going to put in is correct. So let's say that the BMI of this person is 280. Let me use 211. Another one is 3781. Then this one is 1672. Okay. And then the height, let's say the height is 1.2, 1.3, 1.6 meters. Now, look at the range of the data. You see that this one has a certain range. This also has a certain range. And this also has a certain range. Technically, this range is, the range of data you have here is way too much. Meanwhile, the predictive model that we are going to build is going to combine all these data together, a collective power of the input data in order to predict the output. So we have something called bias. Because this one, the range is too much, 2,000, 3,000 as compared to just 1.2, 2.3, and then 1.6. It may create a lot of outliers, increase some bias. It will tilt the data, or the bias will be tilted towards the BMI because the BMI data is very huge. They're all huge. So to avoid this kind of biases and this kind of issues and this kind of challenges, that is why we say, let us scale it or standardize the data, put the data in the common standardize the data or scale it from, let's say, from 0 to 1, meaning that no matter the range, even if this range is 2, 6, 7, 8, whatever, maybe even millions or what have you, you are going to scale it to in between 0 and 1. None will go beyond 1. That is what we mean by scaling. So when you scale all the data to a certain range, your own defined range, then it avoids or eliminates certain biases in terms of your prediction. That is why it is important as a data scientist, always try as much as possible to scale the data. Sometimes the kind of data you're working with, maybe the ranges may not be too much in a way that you can go ahead without scaling or standardizing the data and make your prediction. You get good accuracy. But sometimes the data is in such a way that the biases, or let's say the ranges are too much, the differences are too much. So in this case, there is a need for you to scale it. Compare the BMI and then the 1 point, the height 1.2. You realize the difference in terms of the ranges. Okay, I don't know whether you understand what my explanation here.
Yes, sir. Thank you.
Yes. So, but here with Sklm, everything you need to learn. If there's a package that you want to use, come and check it here. Google and you to bring it here. All the information around it, what is it, and all that. You can get it and then go and make the modification. Handle the attributes and whatever. So I'm going back to my yeah. Okay. So now that we have scale, now this is where we build the predictive model. You remember I said the predictive model. I made mention that you can use we can go with the k-fold validation or the test train technique or test training. So let me start with the k-fold validation. So our data is scaled. So now let's use the test train for this. Just a minute. Okay. All right. So the predictive model, we start. So first, we are going to use k-fold validation. To use k-fold validation, then we need to use the package. And there's a package from what we call model selection, because it's part of the model. Anyway, let me just do this. Let me practicalize this. Just say that we use the k-fold validation. I don't want to quote it like that. So let me just come here. Let's Google k-fold in Sklm. I can just quickly write it. K-fold is in Sklm, but a sub package called model selection. Model selection. So when I click on this, so you see here, Sklm dot model selection dot k-fold. Then you can now give your parameters in the project as a class. But to import it here, you see that from Sklm.model selection, we are picking it from model selection, import k-fold. So let me just copy this. I could have just written it, but I just wanted to show you where you can get some of these information to also handle your project. So let me put in here from Sklm.model selection, import k-fold. So we need k-fold to be able to apply on our data. So let's declare a variable here and develop our model. So let's call this variable folding, or you can even call it k-fold, because I don't want to confuse you. So let's call this one folding. Now, folding is equals to, since we are going to apply k-fold, so I can decide to just copy this package called k-fold here, sub package, put it here. So I say k-fold, function. In it, we need to now define the split. You remember I said, if I define the k to be 10, meaning that you are going to split the data into 10. And the example I gave was that we are splitting the data into 5. So the only thing that you have to worry your head on is to define the number of splits. After defining, you can also define the number of randoms that it should do, so that after splitting, it can do several random of the data before it will pick the final data and work on it. You can also choose to ignore the random selection or the random states, and then just define the number of keys, and then you are gone. So let me go back to this side and I'll show you something. Here, you see n splits. Here, they are splitting the data into 5. Then the shuffle, we don't need to do shuffling of the data. Of course, you can define it as 4. And this is not compulsory, but this one is compulsory, the number of splits, because you are doing K-fold. Then the random state is not also compulsory. I can decide to say that the random state, you shouldn't randomize it before selecting the data. I can also say that you should randomize it to 3 or 4. So I can choose not to bring any of this, the shuffle and then the random state, but just the splits. Okay, so let me take this and then go to my project. So let me put in here. So number of splits, mostly we use 10. This one is, no, we don't need this star here. Then the shuffle we see, so we can even define the random state to be 2, or let's say 4. You can even delete this one out. Then like this. So we have the folding. So that's the key fold. We have been able to bring in key fold and define the various parameters, what we want to do with the key fold. We said the key fold split the data into 10, and also have a random state of 4. Now, the next step we are going to do is that we are now going to create a model. So what machine learning algorithm are we going to use? What kind of algorithm are we going to use? So let's say that we are going to use logistics regression. So let's create a model, or we can see that let me use ALG, that's algorithm, or a machine learning algorithm. Okay, let me make it MALG, meaning that machine learning algorithm. What algorithm are you going to use? You remember I said in classification, you can do logistics regression, you can do naive Bayes algorithm, you can use naive Bayes algorithm, you can use support vector machines, you can use decision tree, there are many. Now let's use logistics regression. Now, the same way, logistics regression, we need to import logistics regression in the project. So I write logistics regression is not actually bringing in because we haven't imported it. Let's import it first. So how do you, okay, let's go to this side, the same story. Let's Google logistics regression in Sklm. Okay, so when I click on this, so these are the parameters of logistics regression. So you see Sklm, the linear model, logistics regression, you can define all these parameters. Okay, let me go to a sample project. At a sample project, this is how you import logistics regression. So we say that from Sklm.linear model, there is a sub package in the Sklm called linear model. Because logistics regression is a linear algorithm. So all the linear algorithms are put in the linear model. So let me just copy this. Then go here, go to our projects, and I put it here. So from Sklm, so from Sklm, the linear model, import logistics regression. Now all I need to do is just copy this. Come here to just, and then put logistics regression. Now in logistics regression, we have something called solvers. I know you did it under management science. But solvers are the mathematical component of logistics regression. That will make the mathematical or build a model or make the mathematical computations within the data. So there's a number of them. We have lip linear model and all that. I know you did this one in management science. Okay, so let's define our solver. Okay, we can even Google this and say that solvers in logistics regression. So there are a number of them. Logistics regression solvers. We have one called lip linear model. Okay, they are even here. Let me call lip linear. Okay, so these are, so the class implement regularized logistic regression using lip linear library, Newton, CG, SAT. So these are all solvers. So you can choose any of the solver. First, we can even use the lip linear and check the output. If the output is not that strong, you go and pick any of the solvers. So let's take lib linear. So we take lib linear, then we define, we say that we are using a solver called lib linear, but you need to put the lib linear in quotation, single quotes or double quotes. Okay, so this is our solver. Now that we have the algorithm here, we're also going to do k-fold validation. Now, the next step is that we need to now do our computation, find out the results. So let's run this and see. Okay, it says that setting a random state has no effect since, okay, this will raise an error in this, okay, it's not an error actually, just warn you something. Okay, so we have this and that. Now the next step is for us to, so we have the folding, please just a minute. Sorry, please give me 5 minutes. I need to call this down response. Pause. Okay, so now, so we have our, this is how we have defined the folding, and this is the logistic regression we are going to use. So we go down. Of course, you can also use naive Bayes, you can use support vector machines and all that. All you need to do is just define the kind of algorithm you want to use here. So we are using logistic regression. So let's move on. Now, the next step is that we are going to see the output. The output, we are going to look at the output, and the output is just to calculate the accuracy. So to do that, we say that, let's say, results. Let's declare variable and call results. Let me make it a result like this, equals to. Now, just look at what I'm going to do here. It's very important. We are going to now compete with a cross. Look at the output, use another package. We call it cross-val score. Cross-val score. So let me Google here and say cross-val score. Okay, from Sklm. So let's take cross-val score. So with the cross-val score, you need to now tell us the model. The estimator is the model. That is the model, like the algorithm. Then you have the X, the input, then the Y input. Then of course there are other parameters you can also look at. If you are doing cross validation, then you need to define that, okay, this is the fit, or you are using CV. That's the cross validation CV here, which is also very important. Okay. So now we go here, look at the cross-val score. So you see that from Sklm.model selection, import cross-val score. So you need to import this package before you can use it. I'm going to our projects. Now here, you put cross-val score. So we say that results is equals to cross-val score because we have already imported. Then you open this parenthesis. So in it, we see that here, our model, instead of model, we use machine learning algorithm here. So just copy this machine learning algorithm, put it here. That means that the whole of this one, the logistic regression using deep linear model, comma, we want to throw it on our X and Y. But the X, you remember the Y is the X, sorry, the X is no longer X, but the X is now called scaled because we have scaled it. So our X becomes scaled. We call it scaled, this one, comma, and our Y is still Y because we did not scale Y. So you put Y here. Then comma, it means that we are fitting the algorithm, or we are throwing this logistic regression algorithm onto our X and Y data, but the X is scaled. We could just to make things easier, why don't we put X here and say that X underscore scaled, it will be easier. So in this case, I'll copy this one and put X scaled. Then I'll put X scaled here so that it will be easier to get it here rather than just putting scale there. So the X, which has been scaled, and the Y. Then the next is that, what are we going to do? Are we using the test string, or we are using the k-fold validation? So we say that we use the words folding here, and we defined how we're going to do the k-fold. So let's put folding. So we say that folding, our CV, which is very important, the CV, that's the cross validation, is equals to folding, because we define folding for it. So we have the algorithm here, and then our CV, which is folding. If you go here and check, you see that we have a parameter called CV. Here we put none, but in our case, we are putting we have defined the folding to split into 10 with random state of 4. This one, I don't think it's case sensitive, but let me put here, something like this. So here, this is the outcome, or this is the model we have built now. Now, the next step is that let us print the results. So if you want to print results, the expectation is that it will bring, because it's tenfold, it will print them in 10 different, folds, results. So let me take this results and put it inside here. Then run this. When I run this, so you see that it will give us 10 outputs. One here, this is the results. Okay, let me take this one out. I'm not scaling it, the scaling out. So let me run it again and let's see. So you see that we have this one on the first, you remember I said the k-fold, you divide the data. This time we said we should divide the data into 10. So the first, the X1 divided by the remaining one, the output is this one. That's the accuracy. For the second one, the third, and all the 10. But now I told you that we need to find the average of it. That will represent the accuracy of the algorithm. So now to do that, you say that result dot mean, we find the mean of it. So you say mean, and the mean, of course, you don't give it any parameter. When I run this, it will give us mean, the mean value. So the accuracy of the algorithm is 0.76 now, meaning that it is okay because it is beyond the threshold of 70%. Of course, if you want to add a percentage, all you need to do is to just multiply this one by 100. If you multiply this by 100 and then run it, it will give us 76%. Well, if you want to add a percentage, why not? You can say that here, you can even write that. You can just say that the accuracy is, then you put comma here, so that when I run this one, it will say that the accuracy is 76. And then if you want a percentage, I think that we could, I think we just put comma here, and then put this one and put percentage in here. Let's see whether this one worked. It worked, yes. Okay, so it worked. All right, so that is it. Very simple. And I know that you can do it better than this. There's a lot you can explore. We can change, you can even do the money. You see the results is 76%. So now let's go and change the splits. Let's split the data into 5 and see the results. So that one gave us also 76.051. I think the first one is better than this one. Now let's split the data into 20 and see. So meaning that you want 20% of the data to be tested, be a test data. And this will give us 76.21. So this is even better also than the data split into 20 is better. Not the 20%, sorry, the split into 20 is also better than when it is split into 10. With the random state, you can put 7 here, and let's put 10 here. run this and see. So this will give us 76 points. So you manipulate it, whichever is okay and is stronger in your results, you have to report that this. And if you are working in an organization where you are building this model, then you need to manipulate it and get the one which is strongest. After that, you can now use it. You can use the model to make any future predictions. Okay. So let's see. No. Let me. Okay. Yes. What other thing can you manipulate? Okay, so we can also change the solver. I don't know whether there was with the crossbar. Where is the solver? Solvers. There are other solvers as well which we could explore. Okay, let's use the Newton CJ solver. So you may also want to check with the Newton CJ solver and see. So when I run this, the result is 76.8, and I think that Newton CG solver is better than the lip linear solver. Okay. Now, the next step, or the next thing I want us to look at is the the test train. If you want to use the test train technique, and then we can also do what we can report the confusion metrics. Confusion metrics as well. Okay, so yeah. Let me also do this. One thing about Python is that when you want to comment, you just have to comment everything. Comment the block of it. Okay. No, I don't need to comment this one. Let me take this one out. Okay, because we need this. We need a scaling tool. This was what we actually, this is the K fold. So now let's do the test train and see. How do I do this? This shift here, shift. Of course, even with the, okay, let me do this, sorry. Of course, you can also change the algorithm. You can change this. We use the logistics regression. Let's use naive Bayes algorithm. So we just Google naive Bayes. These are all machine learning algorithms. So let's use naive Bayes in Sklm. Let's see how we can also use naive Bayes algorithm in Sklm. There are a number of them. We have the Gaussian naive Bayes and all that. There are a number of them we can use. We have multinomial naive Bayes. We have the Gaussian naive Bayes. We have the complement naive Bayes, Bernoulli naive Bayes, and all that. So we can use the Gaussian naive Bayes. So let me click on this. So with a Gaussian naive Bayes, of course, we can define this. So we use this one, Gaussian naive Bayes. We don't need to give it any parameter, of course. So we just come here, and then since we use logistics regression, so instead we can say that here, instead of logistics regression, let's put Gaussian naive Bayes. In this case, we don't need a solver in Gaussian naive Bayes, just like this. And then, but what we need to do is that if I run this one to give us an error because we have not imported Gaussian naive Bayes into the project. So this one will give us an error, say that this one has not been imported. So we need to import this one also from the model selection. So is imported from here. So we can just copy this and say that from sklm.model selection import Gaussian GU. Let me just go and copy it from here. So Gaussian Yes, naive Bayes. So let's run this and see the error that will crop up. I think there's a problem. Model selection. Gaussian naive Bayes doesn't have that. No, sorry. We are importing it from naive Bayes, not model selection, because it's not part of the model selection. It's part of the naive Bayes itself. Naive Bayes. We call it naive Bayes. Okay. So it's rather from Sklm dot naive Bayes. Within naive Bayes, we pick Gaussian. So let's run this and see. So there's something wrong with the spelling. Okay, so let me quickly go here and just pick it from here. So from Sklm naive Bayes. So and then I think it's all caps A, lower. It's small n, not capital N. So let me quickly go here. This one should be small and not okay. So let me place this one here. Okay, so we run this and see. So when you run, you get an accuracy of 75, meaning that naive Bayes performance is lower as compared to logistic regression. So logistic regression performs better on the data than the Gaussian naive Bayes. Of course, there are other multinomial naive Bayes, for instance. And then we could also just come here and take multinomial naive Bayes. This Gaussian. Bernoulli's, but you need to read under them how they are used and all that. Okay, and then of course we have another machine learning algorithm called support vector machine. Support vector. It's a classification algorithm. You could also Google that. So support vector machines under classification, which has different kernels. Okay, so SVM, call it SVM. Okay, so without talking much on this, let me quickly take you to the test train too. So I am just commenting all these. So let's see. Now another comment here. So this time we are going to use the test train technique. Test train approach. Okay, so with that, we start. First of all, you need to define your X train. We are going to divide the data into X. You have the X underscore. So in our case, we are not going to use X train. We are going to use X. No, we are not going to S scale because the scaling, should we use the scale? Okay. So you don't, so we use X train. Let's use X train because we use the scaling data as well. So we say X train, comma, X underscore test, comma, variables X. Then we now move on to Y underscore test. So let me make it small y underscore test, comma, no, train text, X train test, so Y train test. So we say Y underscore train. So these are variables we have declared. So in this variable, we say that test train, we use train test split package. So we call it train, because we have not imported it, that's why it's not showing. So let's go and then import that. So where do you import train test split? So we say that from Sklm, all I need to do is, let me just copy one of this and say that, because the test train, we're actually picking it from model selection. The same way, please, all you need, just go and Google it and it will come. So we have from Sklm model selection. So from Sklm model selection, we are importing train, underscore test underscore splits. See, there's an error somewhere from Sklm, one error. From Sklm, no, we are not, it's model selection, not linear model. Sorry, it's a mistake. It's rather model selection here. So model selection, okay. So in this case, let me start again. So Sklm dot model selection imports train. So it's here. So now that we have train, test, split, meaning that we are going to split the data into train and also test. So you need that package to split that. So to do that, we put this one here. Then we have our open and close bracket. So what are we going to do now? So what we're going to do is that we are going to say that we have our X, our data, we define our data. Our data is X, comma. But in our case, we are using the X scaled. So X scaled, S scaled for the X value and a Y. We didn't actually scale Y, so Y. And then we need to also talk about the target size. The target size, meaning that target size underscore size is with the test data, what is the percentage that we are going to use for testing. So if you are using 20% for testing, then we say that 0.2, meaning that 20% of the data is going to be used for testing. And then we also need to define the random state. That is, if you want to, but it's not necessary. You know, I told the random states, you can randomize it before the final output will come. Sometimes it gives better accuracy, but let's leave the random state for now. So meaning that here, the scaled X data that we have, and then the Y, and here we are splitting the data into 80, 20, but you define only the 20%, the one you are going to use for testing. Now, the next step is that what algorithm are we going to use? So let's say that we are going to use the Gaussian naive Bayes. So I use machine learning algorithm with the Gaussian naive Bayes. That's what we are going to use for our data. So in this case, we need to fit that into the project. But before we fit that into the project, we need to say that our model, the model that we are going to develop is equals to this algorithm, the Gaussian naive Bayes, which we are using MAL. This one, let me copy this one and put it here, because that's what we are going to fit the X scaled and then the Y. Sorry, the X. We are going to fit the X train and the Y train, because this time we are defining what we are going to use to train that algorithm. Please, confusion ayabasana. The class is quiet.
Yes, doc. I have some way, doc.
Yeah, okay, you let me continue, because since I'm recording, I will send these recordings to you, and I think that it will help. So, so machine learning algorithm dot, we are going to fit it. So you can choose this. So what are you fitting on? We are fitting that on only the training data, and the training data here is X. So we say X train, because we have training data for X, we have training data for Y, comma, and then the Y train. And the Y train. So let me run this and see the output. So it says that invalid target size. Just a minute, what is wrong? Okay, so X train, yes, train is equals to so we have the X train, test, and then train. So we have this, and it says that in train test split, raise error. So invalid parameter pass. Okay. String options. Invalid parameter pass. So target size. Okay. Why is target size? Because maybe I could just go and Google it and then take it. Target size. Okay, let me use extreme. Let me use the x, because I define xy. Okay, let me use the xy directly and see something, because it should work. Why? It has no bearing on that. Okay, we are using x. It's rather underscore. It's okay, underscore scale. Okay. So now we have x train, x test, y train, y test. So what is wrong? Let me run again and see the error. Okay. There's something from the charts. Nanadrua, I say yes. What is the problem? Okay, when I run it, options. Let me, this kind of, maybe probably some typo error somewhere, because this one has been defined already. Test train. Let me quickly, let me pick this one and then put it there, just correct the error. Okay, yeah, it's it's a size. It's test the size rather, not. I think I made a mistake here. This one is rather test size, not test target size. Oh, let me run it. Let's see the outputs. So one error is corrected, and then we have error found input variable with insufficient number of samples. Okay, so so x string text string, this scaled y-x text size. So what is, okay, let me see where exactly the error is coming from. So I put this here. Let me comment this one as well. Let me run this and see where the error is coming from. Okay, so there's not, okay, so in this case, let me open up the algorithm, so this is correct. So open up the algorithm, that's also correct. So here is where the problem is. Model is equals to this x train, y train, x train, y train. So why is it wrong? X train, y train, x train, y train. Okay. Okay, let me take this off and run it again and see. Why is that giving an error? We have the model here, we have the mark.Gaussian, which we are fitting onto the data. So we are fitting that algorithm on the X train and the Y train. So is it that, let me take this one here. There's a spelling mistake here. Then the Y train, Y. Okay, so let me run this again and let's see the outputs. Okay, so it's correct now. No, there's still an error somewhere here. Okay, this error may not, okay, let me see. We have, okay, so we don't need, okay, we have transformed the scalar transform, we got this x scale. Yes, that's correct. Where is this error coming from? Who is calling me? Okay, so we have inner return, check constant length, found input variable with number of found. Okay, so the problem is here. Let me put comment again and see, run it again and see why it's. Okay, so Gaussian. So why is this one a problem? Okay, let me just quickly check this project. I think I used it before. So the model fits. So why is it not? This is it. Ah, okay. Yeah, I get it. You know. Yeah, the problem is that you need to fit it on the model. So model.fit, but we are using this. Okay, so I define the model here. Yeah, so model fits. And so what is wrong? What was the error? Let me check here. Ah, okay. Yeah, so model fit. Yeah, that's correct. Okay, let me take this out and put something like let me call this one models. Okay, so mag.fit. Yes, so this is correct. Why is giving an error? Models. Have I defined models somewhere here? Machine learning.fit. X train, Y train, because we define the variables here. Okay, let me use X directly here. Sorry. Let me use X directly here. And then maintain this. Okay, so let's call this one models. And run this and see. Okay, so that was what is the problem? Okay, so careful. Let me take the whole of this one out and see something. Test train. Okay, so I know that the problem is from here.
What about maybe the X train, X test, Y test?
You know, we are fitting the model only on the training data, but not the test data. Only the training data. And the training data, you must have the X and the Y. Okay, yes, the input, the X train, because the training there, you know, we define that X train, X test, Y,
Yes.
Y.
Train.
So we are interested in the training data, not the test data. The test data will come. So we are fitting this model on the training data. That is correct. But I don't know. Let me see. So models, we only declare a variable models. Then here we said Gaussian naive basis, MLG. So this one, or we could just see, if I see model here, this one dot fit. So we are fitting it on the training data. So X train and the Y train. This is one of those things. X train, Y train. So what is wrong? Because this is correct. Oh, so we have something is wrong. I should just figure that out here. X train, Y train. Let me check this project. What is wrong? So, but this was just a for loop. I use different algorithms. So, okay. So after that, so model fits. So we declare variable model fits X train, Y train. It is after that we can now use it to predict the test data. What is wrong? So after that, we can now see that the predicted, you know, what we are looking for.
Doc.
Yes.
I'm seeing something. I don't know whether spellings are also a problem, right? Because I'm seeing models, but in the other one, I'm seeing model.
Okay, no, but this one we decided to use model, but of course I can even make it model, but
Okay.
yeah, that one is a different project. So why? Okay, if I look at the error too, it says that validate. Okay, is it that one of the X is it capital? No, they are all small X. And why? What is happening? Let me see. We scaled it, and then we got a. Even with this, it's supposed to be because we are actually using X. We are using X scaled, so we are not using the original X. So the Y, the test size is this. So we have this, and we are using Gaussian. Okay, so model. Okay, okay, it's possible. Okay, I think that we need to import a package. we need to import the fit package. Yes.
Doc, I'm
Yes.
still confused. Okay, it's the X train, X text, X Y train,
Yeah.
and Y test.
Yes.
I think you have swapped them all.
Let me see. Where?
You have swapped them. See, X train, X test. It should be Y train, Y test.
Which one? You mean here?
Yeah. Yes.
X train, X test. Okay.
Y train,
Yes.
Y
Yes.
train,
You're
Y
right.
test.
Yeah. Okay. That could also be an error because we need to we need to have this training first.
So
So
Y train should come before Y test.
yeah, so let me just quickly, yeah, you're right. With a test string. So let me just pick it from here. Okay. So okay. So we have the X train, yes, the X test, they train the text, then they train the text. Okay. All right. So let's run this and see whether that one takes care of the error. I think that was the error. Okay. So right. That was the mistake. So the arrangement, because you have the training, the test, the training, the test. Okay, that's correct. So we have the model, the mark.fit on this. So the next step is that we need to what do you call it? Make our prediction now. So now that we use this to train, so our prediction. So we say we can use a variable called predicted and say that the predicted is equals to. So this time we are not using. We are using this model because already we have fit this algorithm on this. So we say that model, that's this model. Dot. Now we are going to predict X. So we are now going to make our final our prediction. So we say predict X test. So X test. So predict X test. Okay, so we run this and see the output. Whether there's an error. No, there's no error. So now that we have our X test, we have predicted. Now let's look at the final output. So the final output, we can first of all look at the rock. You can come out with a rock, or better still, I've deleted the first one. Okay, we come out with a rock. Rock is receiver operating characteristics. I don't remember. I think I did explain that to you or something. And then also what we call confusion matrix. You can also calculate and come out with a confusion matrix. But let's calculate, let's output the accuracy, which is also rock. So we say rock is equals to, there's a package, sub-package called rock under curve score. We need to get rock under curve score. And to do that, we need to import that. So let me go and look for rock under curve score here. Yeah, this one. It is imported from matrix. I could have also Googled that. So in Sklm, we have matrices, import rock underscore this. So in this case, I can say that rock underscore this, the score. I need this score. So in this case, I am going to throw this or find a score based on the Y test. Based on the Y test, and then which is the original Y value from the text, and then the predicted, this one, where we actually fit the model on. So with this one, you can say that print rock, let's print rock and see. So when I click on that, it will give us the rock, which is 0.6%, which is tantamount to the accuracy. So we can say that dot mean. Then we bring this. So if no, we don't need a mean. Sorry, we don't need a mean because this is not keyful. So all we need to do is to just multiply this by 100. Multiply this by 100 to give us percentage. So 77%. Okay, that is for the test string. But what I did in this project was that I was testing several algorithms, decision tree, Gaussian, naive Bayes, and k-nearest neighbor, and a support vector machines. So I needed to know the accuracy, and based on that, I needed to use the loop, for name and then model in model. So because I was doing a lot of different things at the same time, I used for loop. And then eventually, I came out with the calculated the plots, find out the most important attributes from the data. Okay, so you can go and explore further. So this is how test train also works, especially with. So let me take I have deleted the first one. I wanted us to probably use the same algorithm with the cross validation to see if the outputs are equal. All right. So any question? Mary, are you there?
Yes, Doc, I'm here.
How's life?
Life is okay, Doc.
Yes, but I'll give this one to you. In fact, this recording, I'll give it to you. So this is how you build the predict. But we can advance that, because this is just part of the course and it's preliminary. There's more we could explore, do more things, do what we call hyperparameter tuning. This is just the raw, script that you write, but you can do further and look at the what we call hyperparameter tuning, and then we could also generate some visualizations in both 3D and also 2D, whatever. But this one should give you the base to build upon it. Please, if you are someone who's interested to understand this one very well, kindly explore Sklm. Everything at all you need to know is here. Even if it is regression, what we did is just classification here. What we are doing is classification. We have regression, we have the clustering. This is why I said the data doesn't have tags or labels. So you are throwing clustering algorithm to cluster the data, look for patterns within the data. So examples of clustering algorithms, you can talk about k-means. We have the mini-bat means. These are all part of the k-means algorithm. We have hierarchical clustering, spectral clustering. We have agglomerate clustering. These are all clustering techniques. So that is for clustering. So you see that what we are doing is just a small part of classification. It has all the packages. You see the naive Bayes, the decision trees, and then we have another one called feature selection. So I use feature selection to be able to. You can use feature selection to select the features with higher predictive model for the algorithm to learn. So these are all things you can explore based on the basis that I have given you today, so that you can advance your knowledge in the area. Let me see. There's a project I was working on. What is the name of the work? I'm currently working on certain work. Let me just touch on this one. Where is the chapter? I said in home. Okay, so this is one of the works I'm doing with these guys. Leveraging supervised. See, if I say supervised, meaning that it's more or less you are using classification, learning, supervised learning. No, this one is wrong. We cannot say supervised learning because being more than supervised learning. So leveraging supervised learning for determining the link between optimal health status and cardiometabolic strategies and approaches. So this is the some of the processes. So the scaling that I made mention of. So data cleaning, do the scaling, then you do feature selection. Not all the features are going to be used. So we use the test train division. So the training goes in the test going here. So we build the model. So what we have just done today is the model and the predicted counts. So this is what do you call it? Artificial neural network. So we explored the various classification algorithms. We have a decision tree here. The naive Bayes. Today I've used naive Bayes, but I use the Gaussian under naive Bayes. We have another one called support vector machine. These are the most widely used algorithms. Then we have the k nearest neighbor. Artificial neural network is also here. This is the confusion matrix. There's no time I could have also explained confusion matrix. Okay, so thank you very much for joining the class. And I know that it's very easy for you. So those of you who want to build more capacity in that area, please go and do more. Go and do more. I tried my best in a way that I could bring in machine learning into this software engineering course. You know that machine learning alone